You'll be on that clock right there. That counts down. It'll count down from 25. I appointed myself chair this morning so that I can embarrass you all. And don't worry about it. That you can use the clicker here. And your mic's up. You got your water on. Yeah, the little green light.
So yeah.
Now you're right. Okay. You can say to me will be recorded.
All right, testing. Yes.
Oh yeah. Jason has deliberately tried to mix it up. I need to be able to sit behind us line of yes.
Okay, when Leonidas sits down, it's time to start. There he goes. Okay. I just have one little bit of housekeeping, actually two little bits of housekeeping. First thing is there's a door over here, and so if you sit on this side of the room, there's a decent chance you'll get to coffee before all the people who are crowding that side of the room. It's a universal fact about this room that most everybody sits over there, so don't be shy. There's plenty of space over that way. Second thing is we're having some of the do-it-yourself sessions this afternoon, starting around 1 o'clock, so you have time to grab lunch and come back and see how to do simulations with ExoSim. And Rhonda, are you today or Thursday? So ExoVista is the other one today, that's right. And that'll be right here at 1 o'clock. Okay, so we have 3 invited talks this morning, and we're ready to go. We typically measure academic careers in terms of H indices, or universities will do it in terms of grant dollars per square foot, or awards or something like that. But my favorite measure, because it's the one I strive to live up to, is how many seeds are you planting for the next generation to grow into? And by that measure, I think you'll find that our next speaker is one of the prime movers in the effort that we are here for today. So it gives me great pleasure, with so many of her students and postdocs in the room, to introduce Professor Vicki Meadows, who's going to tell us the story of astrobiology with HabWorlds.
Thank you so much for that lovely introduction, Jason. Okay, so we're going to be talking about searching for habitable worlds and life with the Habitable Worlds Observatory, and it's an enormous privilege to get to talk about this, because like Carl yesterday, I also remember TPF and SIM and ExoC and all of the mission concepts that we have developed over the last couple of decades and more, and it's just such a thrill to finally have something on the books that can potentially do the type of science that we want to do with astrobiology. So astrobiology is a visionary and synthesizing theme for NASA. I hope you've already picked that up. It runs through our exoplanet science, our solar system science, and of course, the astrobiology efforts at NASA as well. And it now underpins quite a few of our NASA missions, including Habitable Worlds Observatory. So when we talk about exoplanet astrobiology, we're trying to find life in the universe, trying to figure out whether we're alone in the universe by looking at exoplanets. So when we do that, the sort of two major questions we want to ask ourselves, do exoplanets exist that have the right conditions for life? Are there habitable worlds out there? And once we found those, are there planets out there that have life on them? It's not always a given that a habitable planet will have life on it. At least that's our going-in assumption. So if we look at that first scientific question, do exoplanets exist that have the right conditions for life? Well, we've made some baby steps into the pool. All right, so sure, we have Earth-sized planets in the habitable zone. Those are now known. So we have planets that are the right size or even the right density to potentially be rocky terrestrial worlds. They're sitting at a distance from their star where we think they can maintain liquid water on their surface. But as an astrobiologist, that's not good enough. There's a potential there, but the question is, are they actually habitable? Okay, so it's been postulated that surface habitability is much more likely within the habitable zone, but there's absolutely no guarantees that that is true. Okay, so for example, stellar evolution may drive early atmosphere and ocean loss off of a planet, leaving you with a really crazy composition that's maybe more like Venus or has a high O2 atmosphere. And if you look at that, and in this plot here, we're showing TRAPPIST-1e simulated with climate photochemical models to show the surface temperature of the planet. The green ones are habitable, the red and blue ones are not. And you can see that even at that habitable zone position, depending on the composition of that planet, it may or may not be able to maintain liquid water on its surface. So are they habitable? Now the next question, of course, is the habitable zone really a thing? Okay, so we've built up a lot of our field around this construct, right? So now's our chance to potentially go and observationally test that idea. And by the way, I like to call it the light on water zone. I think it's amazingly evocative. Light on water is one of the most beautiful things on our planet. And I think it's something that, I want to look for on an extrasolar planet. This was first put forward, as far as I know, by Kevin Zanley, so I want to thank Kevin for that. I also do it in self-defense, so that solar system icy worlds people don't come up and crash tackle me for my definition of the habitable zone, okay? It's like, sure, you have water, but is there any light hitting it? That's what I want to know, okay? So we're talking about surface oceans. So if that's the case, if we're looking for surface oceans, and we need that because then photosynthesis is out there and, the biosignatures are easier to see. But surface oceans and atmospheric water would be more, in our hypothesis of the habitable zone, surface oceans and atmospheric water is more likely within the habitable zone and not external to it. And then our definition of the habitable zone says that we can cycle carbon so that when a planet gets colder, we get more CO2 in the atmosphere. So therefore, we would expect CO2 in the atmosphere to increase as a function of distance from the star within the habitable zone. So those are two observational things we could go and test. The other thing we might like to do is go actually after light on water. So to try and look for glint in the oceans, and we had a fantastic talk from Sophie Vaughan yesterday about looking for that, and also rainbows and other really cool stuff. But this is work done by Ty Robinson here during his PhD. But essentially, if you have a planet that's sort of behaving like a Lambertian scatterer as a function of phase, it would follow this red line. What you see here is this bowl, which is the actual behavior of the Earth, and you can see data points here from Earthshine on that. That bowl shape is showing you that as you move towards crescent phases, up here, the Earth's reflectivity deviates very strongly from Lambertian scattering, and that's due to both forward scattering from our clouds and also due to glint off of the ocean. So that is the signature. If you can get observations of brightness as a function of phase, you might see that anomalous behavior as you get towards crescent phase. The other thing we care about is, what processes actually govern the acquisition, maintenance, and loss of habitability. So we know that, and I'm in violent agreement with David Singh here, that we absolutely have to understand all the other planets in the solar system to understand something about the evolutionary history of our planet. And it can also reveal things that feed back into our knowledge of the planetary properties of the habitable planet we're looking at. But by far, I think the most important relationship is that parent-child relationship between the star and the planet. So interaction between star and planet can govern whether or not the planet gets to keep its atmosphere and ocean, and also, whether or not biosignatures are destroyed, enhanced, or mimicked by interaction with the star. So that's just a super important relationship. If we fill out all of these different relationships that affect habitability and look at the sort of things that we have to observe, the sort of things we have to understand, this is what's called the planets are hard diagram. But taking truly to my heart the wise words of Professor Natalie Hinkle, we're all in this together, so don't be frightened by this diagram, okay? I think that was really the best part of the conference as far as I'm concerned so far. Okay, so we have a lot of work to do to try and understand whether all of these different factors are going to affect our habitable planet. So the other thing we need to not worry about, again, somebody said habitable zones are four-dimensional, right? We need to worry about time and how terrestrial exoplanets actually evolve around different stars. We've got one example of a terrestrial planet evolving around our G dwarf. We can go back in time through the rock record and the biological record to try and understand what happened on our early Earth. But other planets are going to have a different experience. So in this simulation that was put together by Laura Schaefer and her partner, if you look at the Earth, that green zone's the habitable zone. You see as time evolves, the Earth pretty much stays in the habitable zone the entire time. But if you look at Proxima Centauri B around an M dwarf, you can see that, in fact, it's very much interior to the habitable zone in the Venus zone for a long time before its star cools, it contracts off the main sequence, and its luminosity goes down. So once its luminosity goes down and it's on the main sequence, you finally see Proxima Centauri B pop into the habitable zone there. So to understand worlds and suns in context, which the decadal asked us to do, we'll need to study planets at different stages of evolution, orbiting both M dwarfs and more sun-like stars, the FGK-type stars, because there's this different stellar luminosity evolution. There may also be a K-dwarf advantage in habitability versus M dwarfs and in detectability of the O2 methane pair versus G dwarfs. So maybe K-dwarfs are an area we also need to explore in more detail, although you should see student Megan Gianluca's poster about potentially building up more abiotic O2 and being able to retain it on K-dwarf planets. So that's another interesting thing to look at. Okay, so stellar evolution impacts atmospheric composition, climate, and habitability. The star is so important. So over here, we have our little planet, a little M-dwarf planet in the danger zone early on. It's got a superluminous pre-main sequence star. Potentially, it's losing its atmosphere and its ocean. All of that's happening. You lose the water. You potentially build up oxygen because the water gets photolyzed, hydrogen escapes to space. The O2 is not as good at doing that. And again, as I showed you earlier, you end up with potentially very different types of atmospheres in the habitable zone. And the nightmare scenario that worlds like TRAPPIST-1, for example, having gone through this process, may in fact all be Venuses right the way through. Okay, that's potentially possible. So again, they're in the habitable zone. Are they habitable? Okay, so if we look at, other planets out there that have life on them, obviously, the first thing we want to do is look for things we call biosignatures. So that's really life's impact on an environment. How can I tell that life is operating in an environment? So there's a bunch of ways we can look for that life operating in its environment. We can look for targeted biosignatures for metabolisms that we know here on Earth, things like oxygenic photosynthesis or methanogenesis. We can look for, and this is relatively new in our field, agnostic biosignatures. Agnostic biosignatures are essentially a planetary anomaly, a disturbance in the force, something in the environment that you are looking at that makes no sense from a geological or photochemical perspective. It is the sort of the not planet. You're looking for a not planet. And in that case, it's fantastic. It opens you up to being able to detect processes from life not as we know it, but it means you have to understand the environment exquisitely to understand that something is anomalous and something is not working. And then, of course, there's technosignatures, which Ravi talked about yesterday as well. So, a civilization doing technology is life impacting its environment. You could have things from Dyson spheres, or you might even have climate engineering. If I look at the TRAPPIST-1 system and every single planet in the habitable zone has exactly the same surface temperature, I'm going to be pretty suspicious. Okay, so when we look for biosignatures too, I just want to clarify one thing, which is that we often talk about looking for these disequilibrium pairs, or looking for a disequilibrium. But the disequilibrium is just a flag, and it says, hello, something's odd here. Okay, so the disequilibrium is the thing that tells you to go and look and try and determine, I'm seeing things that I shouldn't see because in the equilibrium state they would be gone, and yet they're here. So clearly there's a flux of this thing coming into the environment that I'm looking at. What is that flux? Where is it coming from? What is the magnitude of that flux? And that's when we can start to say, oh, I've got this massive amount of methane coming into the atmosphere. And on our planet, methane from biology greatly outweighs methane from geology. And so there's certain limits where if you have very high methane, you might say you're looking at life. So we might look for these equilibrium pairs, but we also have to understand, is there an active flux there? And to understand whether or not the flux is active, we also have to understand the destruction processes from the star, for example, photochemical destruction from the star. So the other thing we have to do, again, working towards this theme of sort of understanding the biosignature in the context of its environment, is we're looking at, other molecules in the planetary atmosphere that tell us that actually a photochemical process is potentially acting here to get us our biosignature. Maybe CO2 is being split up into oxygen and CO, and it's very stable. So there's different types of environments where that might occur. So when we detect a biosignature, that's not enough. That's just the first step. After that, there's a whole assessment analysis that happens. Okay, so There are two paths for searching for life on exoplanets, and this is based on this was actually, I guess, preserved for all time in the NES 2018 Exoplanet Science Strategy. So we have what's called the M-dwarf opportunity, where we have transits and high-resolution spectroscopy in the 2020s with Jwst and ground-based telescopes. We will have a limited number of M-dwarf targets to be able to look at with this. That's the main constraint. We can do transit eclipse and direct imaging spectroscopy. But transit, because of things like refraction, also just the intrinsic opacity of the atmosphere, will mean that we can't get down to the surface. If you're coming in at a slant path in an atmosphere, your ability to see the surface is compromised versus a nadir view, which you get from direct imaging. So transit will sample the upper atmosphere and above. We will study a few targets in detail over a long time. So we will have our golden targets, and Travis 1's definitely one of those. But, you know, we'll be limited. For the 2030s and beyond, what HabWorlds starts to open up for us is being able to look at FGK M-dwarfs together. So more sun-like stars, ones that haven't had this pre-moon sequence superluminous phase. And so we can get potentially a larger FGKM sample. We'll be direct imaging straight down to the surface. So we'll see near surface and atmosphere and surface. And also it'll allow us to get a statistical understanding of habitable zone exoplanets. I mean, we'll have to be super lucky if any of the TRAPPIST planets are habitable, for example. Okay, so why do I keep saying we're not going to get very many targets early on for the M-dwarfs? Well, you remember transit, how, you know, planet blocks the star, and if the star is small, then the signal is larger for the planet blocking it. Same thing for the atmosphere, that tiny little onion skin ring that we're trying to detect on a terrestrial planet. It also will produce bigger features if it's blocking a smaller star. And so here in this plot, we're showing self-consistent Earth-like atmospheres around different types of spectral types of stars, going from a staggering range from M8 to M3.5. Okay, and so you can see that the M8s and the M6s produce features that are about, you know, 80 parts per million, something we'd have, you know, a hope in hell of actually seeing with Jwst. The M3.5, we're guddling around down at a few parts per million. So we can really do only atmospheric studies on very late type M-dwarfs. So that's why we're going to be limited. So moving very briefly into what Jwst will be able to do, and I'm going to go through this very fast, which is we will look for signs of ocean loss, O2, O2, molecules hitting each other, maybe signs of HDO even on some of the closer in planets. But actually detecting water could be quite challenging. So trying to detect habitability itself is probably harder than trying to detect not habitability. Looking at biosignatures, oxygen is hopeless. I put challenging up there just to be diplomatic. But basically, you'll need way more than 100 transits, and it's just not just me and my group. There's like multiple groups here who have now simulated this with different models, and I think it's a pretty firm conclusion that at least for an oxygenic biosphere, that's going to be difficult. But the CO2 methane disequilibrium I talked about having larger fluxes of methane, that might be relatively easy. It will still be the hardest thing we've ever tried to do, but it is relatively easy and compared with oxygen. And in fact, the really cool thing is that CO2 methane biosphere might be visible all the way through the actual life cycle of our star. We can actually see the methane biosphere now better than we can see our photosynthetic biosphere in the simulations. Ground-based telescopes will also get us there with high-resolution spectroscopy to try and look at these types of worlds. And Miles Curry has a paper out on this as well, just looking at different types of things we might go after. So, for example, again, that CO2 methane biosphere might be something we might go after. However, for transmission from the ground, it's going to be extremely challenging. There's a recent paper by Hardegree-Ullman that sort of talks about 50-year campaigns to try and get, for example, oxygen on certain planets. So that's going to be challenging as well. So let's go to what we're all really interested in. So if we go to habitable worlds now, what we will have is potentially many exo-Earth candidates. So we go from being limited to our M-dwarfs and maybe only a few that we can get atmospheric features on to having a lot of targets that we can look for. And so that allows us to get the sample that increases the probability that we might, in fact, even get just one Earth if, you know, Earth-like planets in the habitable zone. If only 1 in 10 of them actually has an ocean on it, we should still be, you know, 95% certainty that we get at least one of them to study. Hopefully it's more than that, but at least we've guaranteed against that, not having one. So there's a strategy. I'm just using the LUVOIR strategy here, and I should have said this is from the LUVOIR report. But the idea is, you know, to have this initial 2-year survey that Carl also talked about, where you go and look for targets. You know, LUVOIR will find pretty much its own targets. It'll be looking for terrestrial planets. And it will be characterizing them with multi-source photometry, constraining orbits, you know, and then searching for atmospheric water vapor in their atmospheres So the interesting ones, they then get followed up with a detailed characterization, which includes characterizing the activity level of the star, determining planet masses, searching for biosignatures, searching for false positives, and then just doing more sort of atmospheric characterization or surface characterization of the planet. So if we do that, we will find hundreds of planets around FGK M dwarfs. And the column to look at here, and also the fact that they are across a very large amount of spectral types. So we look at this column here because LUVOIR A is not for us. So if we look at this, LUVOIR B will be much closer to what we get with HWO. And I'm also, checking against the recent Mamajek and Stapelfeld thing, you can see there's a distribution of sort of FGK M targets that we may be able to get after. But as we find the habitable ones, the other ones will just appear. HWO will also have the advantage of being just more sensitive to near-surface water abundance. So this is work done by grad student Sam Gilbert. And she has looked at, here's our ability to retrieve water vapor abundance, and it's sort of the precision that we have for that from direct imaging versus transmission. And you can see we can just do a better job of constraining water vapor near the surface and more precisely with direct imaging. Going after ocean glint, for example, may be possible. So we have the albedo so this way, this is something that Jake did, which is really very clever. So we heard from Sophie yesterday looking at glint and rainbows and a bunch of different things. But Jake actually took two different techniques. One was actually mapping the planet, so watching it go through a bunch of different phases and being able to map longitudinally how bright it was as we saw different parts of it exposed. And if you do that, you can actually separate out into potentially, for our world, two phases. Sorry, no, I shouldn't use the word phases because it's ambiguous here. Two types of surfaces. And those surfaces, for example, the orange one here is solid rock. It's continents and whatever. You can see as a function of phase, these two lines pretty much land on top of each other. But for the oceans, the two phases show a marked difference in their behavior as a function of phase. And by pulling them out as separate types, you're able to potentially have much more sensitivity to the ocean that way. So Jake also looked at how many targets we would get as far as yield is concerned, and the answer is sort of 1 to 10 detectable oceans for a 6 to 15 meter mirror. So there's some incentive for you to get that mirror bigger to be able to get our light on water. And that's actually pretty comparable to Sophie's 4 with HWO and a cloud-free Earth. We did have clouds on our Earth, by the way, and because the clouds are patchy, we're still able to see glint. Okay, another thing we can potentially do is statistical tests of the habitable zone, and this was a white paper that was put in by Jade Claire. She was a grad student, but this idea of potentially going after trying to see whether CO2 actually increases as a function of distance within the habitable zone, and also potentially looking for water vapor or albedo changes that are characteristic. Oceans are very dark. Clouds and ice are very bright. So maybe you can try and get kind of a bit of a very rough handle. So instead of going over everything about one planet, you simply observe one characteristic from a statistical bunch of planets and try and get an answer that way. And then, of course, finally, yay, a clean detection of oxygen from HWO. It's kind of, one of the things it's really famous for. And even when oxygen had not risen very high on our planet, even if there's tiny amounts of oxygen as we had in the Proterozoic, that still gives us a really strong ozone signature. And so in the ultraviolet with HWO, we might be able to see, a very nascent, a very small oxygenic biosphere as it starts by being able to look for potentially ozone. We may also see seasonality as well in that. Okay, so with HWO, we can look at a broad range of life across many different eons, which is fantastic. And this slide is for David. We will never forget the transits. So HWO can also do transits. I have to say, all these pretty terrible looking points here are JWST. And then the points that are all hugging the actual model layer are coming from HWO. So we'll be able to do very nice transits and also down into the visible, which is complementary, of course, to what JWST can do. All right, so wrapping up quickly here, I was also asked to talk about the biosignature assessment framework. Okay, so when we find or think we found life, there's a number of things we need to do. And we held a workshop with a very broad community, people who do sort of studying early life on Earth versus, trying to look for life on Europa and Mars, as well as us exoplanet folks. And we came up with a framework of what we would do when we detected something. And part of it is sort of looking at, okay, first of all, I've detected it. What do I ask myself? And then once I'm absolutely certain I've got something here, what do I do to assess whether or not this is in fact due to life or it's a planetary process? So we came up with 5 questions. The initial 2 questions on the detection, have you detected an authentic signal, or do you just have some weird spike or some bad flat fielding or whatever? Have you actually got a signal here? Have you adequately identified the signal is the other thing. So that can potentially speak to, do I have the right resolution? Do I have overlapping bands? Do I think this is water, but it's actually methane? That's a real thing. Okay, those two overlap on top of each other. Once you've convinced yourself you actually have a signal and it's the thing you think you're looking at, you then go into, are there abiotic sources for my detection? Abiotic meaning not due to life. Is there a way a planetary process or photochemistry could do this? And what are the things I should look for that give that away? Because those processes can be given away. And then, of course, the other quick thing that should be done in parallel, is it likely that life could produce this expression in this environment? Okay? I mean, we should ask ourselves that. If we say, oh, hey, look, this is enormous flux that, is 5 times the productivity of the Earth's photosynthetic biosphere, we might ask ourselves, yeah, that seems unlikely. Can we get to a point where we think that's reasonable? And then we talk about whether or not there are independent lines of evidence that support either of those hypotheses. So we go to the next step of testing the hypothesis. I'm going to skip over this a bit. We do have, if you want to go look at this Heather Graham and I led the community white paper on this. It's up on archive if you want to go and look at a worked example of how we do this for oxygen. It's very complicated, but it was fun. So I just want to sort of finish off by saying that there's a bunch of applications of this for the mission life cycle, and this is something we need to worry about. So when we're trying to look at our signals, confirmation of the detected signal requires planning, knowledge of calibration, background noise sensitivities, having the right resolution, all that sort of stuff, operations and instrument behavior. So you think about that in advance. You think about understanding, sources that could impact your data interpretation, and, whether or not there are procedures and requirements that you need to have to distinguish overlapping signals or ways that you could get confused. Think about that in advance. And then when it comes to the interpretation, we need to be able to have sufficient wavelength and resolution to go for we need to know what they are, what we need to do to distinguish a real biosignature from a false one, and we need to have the capabilities on the mission to be able to do that. So I actually mentioned the science traceability matrix here, sorry, Aki. But I mean, that needs to include measurements to assess, key aspects of habitability in the environment so we can do the assessment. Not enough to detect the biosignature, we have to also do the assessment. And then, of course, be able to take follow-up measurements to go with that. So that might all sound very daunting, but actually it fits very well into the existing LUVOIR model here. And I'll just say that, as you work your way down here, you are still addressing all of the things that are required by that framework. So I'll finish up and say, the take-home message is that while we will start to probe exoplanet habitability and search for biosignatures in a handful of M dwarfs in the near term, only the Habitable Worlds Observatory will provide the sample size required to enable statistical studies of a diversity of terrestrial planets orbiting a range of stellar hosts and significantly increases our chances of detecting and characterizing an inhabited world. So.
Vicki, thank you. Any questions in the room? Surely there are a few. I think we're going to still do the introduce yourself thing because there may be new folks here.
Kaz Beichman, Exoplanet Science Institute. Thanks, Vicki. HWO is going to be hard. We're asking it to be hard across a very broad range of wavelengths. If you have to give up one of your children, which, if you go back to your figure that shows, our very nice spectrum of the Earth, which band, that one, is more important to you? Short word of, 400 nanometers or long word than a micron?
Okay, this is a terrible question.
Thank you.
However, as long as we can get the oxygen band and the water here, I think the short wavelength doesn't have as much information as the longer wavelength here. It is brighter, though. So, there's a huge trade. That's a really hard question. You have to trade off, do I want to get a relatively easy thing that may not give you very much information, or do I want to have the capability to go deep on something that's more expensive, but is potentially more information rich? And I think I'd go for the more expensive, more information rich, trying to get the longer wavelengths. But, there's also the inner working angle and, whether or not I get that choice. So yeah, I would like all of them.
I think we'll be lucky to get one or the other, but I think we're going to, that to me is a driving question for the coronography, not necessarily for the general, say, UV capabilities or whatever, but it's going to be very expensive to do either. Both is going to be tough.
Yeah. I think we still want the UV. We would lose maybe the short wavelength part of the visible. But I hope it's only a hypothetical.
Well, in the spirit of having your cake and eating it too, I have three words, second generation instrument.
Yeah. So I guess that's, maybe we wait for a cake. 2 marshmallows
That's
later.
3 words, yeah.
But some of those are driven by the telescope, not by the instrument, and that's part is tougher to do unless you're going to make the telescope bigger. More segments, I understand.
Okay, any more questions for Vicki in the room? Oh, we have one back here.
Nicolas Flaget from Space Telescope. So you mentioned agnostic signatures. Can you give some example and maybe some that we would be able to detect?
That's an excellent question because you're trying to detect life as we do not know it. So what you would want, you'd be looking for disequilibria that you can't explain. So you would measure a suite of different types of molecules in the atmosphere. You would run them through a couple climate photochemical model. You would think about potential geological sources, and you would find an anomaly in that. So for us, it's an unexpected disequilibrium. And then from that, we have to then maybe go back and say, okay, well, this is really interesting. There's this huge flux of ammonia or whatever coming off of this. We wouldn't be using that, but there's a huge flux of, one of our gases coming off this planet. We can't explain it, any other way. But we would look for disequilibria across multiple molecular species.
Alex, do we have any questions online? No questions online? Okay, time for one more in the room if there's one. Chaz again? All right. Why not?
Surface gravity. How much do you need mass or radius or their combination?
Those are important. I believe they are not as important as you expect for Jovian planets. I don't know. Ty, can you answer that question? Okay, great. And the answer?
You can still engage in a high level of atmospheric composition without operating all the
Right.
So not knowing those in advance is not a good.
So it's nice. No.
Is that true for Earth-like planets? People online can't hear you.
Yeah, so we
sorry.
can't
So
have Vicki address that.
yeah, so Ty answered here that I know Salvador has a poster on this, and he said that you could engage in a pretty valuable assessment of the planet without having mass and size. And so those are nice to have, but not exactly essential. We can still study terrestrial exoplanets without those properties. But, we'd rather have them.
Okay, so we have one last question coming in from online.
Yeah, from Caleb Scharf. An odd question, but can moons of habitable worlds confound spectra and blend with planet spectra?
I guess they could, yeah. I mean, we do have, because if they're close enough, we may not be able to separate that. But you could look for this technique that Eric Agel created, which is sort of the spectrophotometry of the center of light. That's what we called it. Where, as you watch the planet move around its star, you can potentially tell that, that there's actually a different viewpoint on that, and you can see the variability of that, which you can then pull out as potentially two separate spectra. So there are techniques that could potentially separate that out without having the actual angular separation to do it.
Okay, let's thank Vicki.
There's another mic there. Let's go.
Can you transfer that to Evgeny?
Certainly.
All right. So it's my belief that let's make sure we get there. Okay, that when all is said and done, GoMap will not only mature this mission to success, but will prove the value of suborbital and CubeSat scale platforms in doing technology development. Our next speaker is one of the people who has convinced me of that fact, and so I've arranged for her to come and convince you. So we have Evgeny Shkolnik from Arizona State University. Welcome. Let's hear what she has to say.
Thank you. Okay. Is this on? You can all hear me? The light is green. It's all good. All right. Well, thank you for that introduction. I was indeed asked to talk about small sats. But first, I really have to say thank you to Vicki for her inspiring talk. I feel honored that we are here. I hope you feel this way too, that we're really kickstarting something incredible. I look forward to seeing you all at the launch. I recommend we save our name tags and wear them. I'm not, those of you who don't know, you guys don't know me well, but I'm not a sentimental person, but I'm saving this tag, just so you know. Okay. But in general, as we are doing often, we talk a lot about the giant flagship missions, right? And that makes sense because they have enormous costs associated with them. They have revolutionary capabilities. But here I'm going to talk to you about the relatively cheap, albeit absolutely necessary role that small and medium class missions play in the success of flagships, specifically Habitable Worlds Observatory. So, oops, there we go. So I'm going to talk about these three things rather briefly. The science that small and medium class missions can contribute, primarily where I'm going to talk about precursor science that we talked a bunch about already, but also talk about complementary science. This is science that can be done contemporaneously or simultaneously with Habitable Worlds Observatory. I'll talk also about the technology, as you said, suborbital class missions, the rockets, balloons, and now CubeSats are playing an important role in increasing our technology development plans, bringing TRL levels to where we want them to be so that we are comfortable using them on the flagship missions. And then lastly, I'll talk about training of mission leaders, but also mission teams. It's not always about training the leaders. We also have to train people on the team as well. So, when I say small and medium class missions, I am talking about essentially those that NASA already has on offer that are PI led. Okay, so we are talking about the CubeSats that you can propose through annually through the APRA program, the Astrophysics Research and Analysis program, with a cost cap of about $10 million. There's the Pioneers mission, which is relatively new, also, I believe, offered annually at $20 million cap. And I think the Pioneers was actually a response to the creativity of our community in wanting to do more science with small sats. So kudos to NASA for responding to that need. We also have the missions of opportunity at $40 million and at $80 million that are associated with the Explorer calls. And we have the small Explorers, of course, at $150 million. And the medium Explorers at $300 million. And I am not including probes here yet. So if you want to include probes and have a conversation about this in the discussion time, I'm happy to continue that. So I'm not going to get to talk about all the precursor and complementary science that I would love to do with small sats because people have been really thinking hard about this already. There's the XAP science gap list. So thank you to Carl and Eric. I think the latest one is in 2023. I found it online. There's also the SAG-22 report that Natalie Hinkle told us about yesterday. So I'm just going to talk about one example, and this has kind of been a theme we've seen already in the last couple of days, and Vicki mentioned it as well, in precursor science, which we define as the science that informs flagship mission design, architecture, and trades. That's taken from the XEP gap list. So I'm going to talk about, subject near and dear to my heart, but also something that we have heard is really important, which is the stellar context in which our exoplanets that we are interested in exist. And so the example is characterizing the planet host stars, their activity in particular at high energies, across relevant timescales, right? Because we want to understand the planet's formation and its atmospheric evaporation, chemistry, and evolution in general, particularly of Earths that we want to look for biosignatures on. Now, something that people might not totally appreciate is that the timescales that are relevant here range from seconds to gigayears. Okay? And I'm going to walk you through that right now. So let's look at the sun. I'm going to show you just a bunch of data for our sun because we're interested in sun-like stars, but of course we're all stars. We love all stars, but we're focusing at the moment on the sun. So this is, of course, the classic flare shape. So we care about flares that can last from seconds to hours for a very big one. This is data shown from the Solar Dynamic Observatory. It's all normalized here, so I don't have any numbers on the axes, but it's something to understand that we, at many wavelengths, need to understand the flares of these stars and how they impact planet atmospheres. Then, of course, the flares are often superimposed on a rotational modulation. So we know that our sun rotates at about a 27-day period, and there is a modulation that happens there that can impact our spectroscopy, not just from a photochemistry standpoint, but also from a measurement of the transit itself, right? And we talk often about the contamination due to stellar activity in the transit measurement itself. And so we have to take this into account. And it depends also on different wavelengths. Sometimes you have the modulation due to dark spots, and sometimes at some wavelengths, those spots are bright spots. And so you have to know kind of what wavelength you're looking at, what time scale you're looking at, what phase in the rotational modulation of your host star that you are interested in when you're doing your planet observation. Of course, we also have activity cycles. So here is a plot of sunspot number as a function of year for the solar cycles 25, 23, 24, and the half of 25. And you can see that solar cycles on order of years to decades is also important. What if we are looking at a planet, right, it's transiting, we come back 5 years later, it's at a different phase of that star's stellar magnetic cycle. How is that going to impact our observation and our interpretation of what's going on that planet? And then, of course, we have the whole star and planet evolution timescale going from millions to billions of years, because the stars change with time quite dramatically, right? So here, this is for sun-like stars, showing you the evolution across time on a log scale with age at different high-energy wavelength bands, and you see that things can change by orders of magnitude. And this is critical for us to understand, especially in these early ages when the planet is forming. What are the conditions within which the planet forms? Can the planet's atmosphere survive the first 100 million years of the star's evolution? So we need to understand all of this, and Vicki already showed some of the impacts here. So here's just one slide, just looking at age. Here's a plot made by the Virtual Planet Laboratory by Evan Davis, one of Vicki's former students. And you can see a reflectance spectrum of an Earth-like planet orbiting, in this example, an M star, as it ages. So when the M star is 650 million years old, you might get a different planetary spectrum than compared to when it's 5 gigayears old. And you can see that the exact same planet with the exact same atmosphere, just due to the photochemistry induced by the UV radiation of the host star, will give you a very different spectrum. This is just really one example. We have a full parameter space we still need to explore. But the good news is that we know that we need to explore it. Like, it's not one of these unknown unknowns. It's a known unknown, and we know how to do this, and we have to work to get it right. So that's exciting. An example of complementary science might be multi-wavelength observations, where you could have a small sat observing at the same time as Habitable Worlds Observatory, but at different wavelengths, or monitoring at longer time scales. So here I'm defining complementary science as contemporaneous or simultaneous. And an example would be, say, multi-wavelength, multi-observatory flare detections, right? So we've been working, on observing flares at multiple wavelengths, and we see that doing so gives us different information, that we understand the energetics of flares differently, we understand flare physics differently. It's very valuable. And here's just one example of a single flare that lasted just a few seconds from our nearest neighbor, Proxima Centauri. This is a program we had run trying to coordinate multiple observatories on the ground and in space, and we detected one flare with ALMA, TESS, ground-based optical observations, and HST. This was a program led by Meredith McGregor, and kudos to her for coordinating. I mean, the effort that she and the rest of us had to put into coordinating this program was extreme, to say the least. And if there were dedicated observatories for which we could do this more efficiently, we would learn a lot more. But still, we learned amazing things here. We learned that the far UV traces ALMA in submillimeter better than anything in the optical. We learned that you could have time delays in the optical that you don't see in the ALMA wavelengths or at HST wavelengths. So I encourage you to read the paper if you care more about that. But this is just one example of complementary science. And I'm sure those of you who work in other fields could think about other science cases for which a complementary observatory or two or three might help your science case of interest. So, I'm not sure why this looks low resolution here, but here is the astrophysics fleet as of March 30th. This is the latest one that I could find online. And you can see here the very small missions in this curve here, but this fleet includes the large missions and the small missions. And so I wanted to highlight those that are currently in development or flying that are precursor or complementary for exoplanet and stellar science. And by complementary, of course, it's just for JWST at this time. Let's see. There we go. We have TESS, which was a mid-X, which is a mid-X. And as we know, it found lots of planets that we're now observing with JWST. So I think we can genuinely consider it a precursor mission to JWST, even though it's doing all sorts of great science. There's SPARCS, which is a 6U CubeSat that I lead, and we have a few SPARCS team members here too, where we are monitoring low-mass stars in the far UV and near UV to look for flares, and we can stare at stars for a long time and characterize stellar planet hosts that way. There's also the Pandora mission, which is not a CubeSat, it's a Pioneers mission. It was awarded in the first round of Pioneers, and the goal of Pandora is to observe in the optical simultaneously during transits. So you observe the star in the optical while taking a transmission spectrum of a giant planet. And the goal of this is to disentangle the noise of the star that I'd referred to earlier in order to get a better transit of the planet atmosphere measurement. And lastly, this new one, I added this, MANTIS. MANTIS is a brand new APRA program out of Boulder that just was approved. So I read online. So that's public information, where also has the idea to look simultaneously at the EUV, the far UV, and the near UV of stars, and with a baseline program, according to the abstract, that could do simultaneous observations with JWST, right? SPARCS also has that capability as well. So these could be missions that observe with JWST at the same time as we're getting infrared transmission spectroscopy. We can be monitoring the stars. So that's what I'm considering great examples of complementary missions. All right, so I'm not going to spend too much time talking about the technology for two reasons. One is there's already an XEP technology gap list, so kudos to XEP for collating all that information. Also, we have multiple technology talks this afternoon that I'm sure are also going to talk about this, but small sats and, as I said, building on the traditions of balloons and rockets are really great at increasing the TRL levels of the technology that we want. And here are two that I'm just highlighting as examples of those that are have technology development efforts that are directly related to Habitable Worlds Observatory. We have Sprite here that has Brian Fleming is the PI of that. It's also out of Boulder, and they're testing highly reflective and protective coatings for mirrors that if Habitable Worlds Observatory does observe below 120 nanometers, potentially this would be one solution. And SPARCS is also, in addition to our science, we're also testing delta-doped UV-optimized detectors and integrated filters where we have strong transmission in the in-band and high out-of-band suppression, which is what you need for low-mass stars. So again, just two examples of small missions that will be launching soon and working directly for Habitable Worlds Observatory. Lastly, talking about training. When I say training, I'm not saying we're just talking about PIs. There are many, many leadership roles on missions, right? We've got the PIs, the deputy PIs, project scientists, systems engineers, project managers, so many, and especially in a giant one, right, like Habitable Worlds Observatory, there will be many, many leaders. And in fact, I would argue that everyone is a leader and everyone should learn leadership skills, even if you're not formally have that in your title. And so I just lifted this slide that I made 2 weeks ago for the Learn Forum. For those of you who don't know, NASA has this excellent virtual and in-person Learn Forum for small sat mission leaders to come together and share lessons learned. And so this is a template. They sent me this and said, please fill this out. What are your top 3 lessons learned for SPARCS? So we could say, right, what are the classics? Test early and often. Redundancy is key. What's another favorite? Mitigate your... or control your margins, tightly, and whatever, right? We have all those. But when I sat down to fill this out, I think that the actual top lessons learned are all about the people, because fundamentally it's the teams that are doing this, and it's the people who are going to fix all the other problems that we have, all the technical problems, it's because of the people. So here are the lessons that I took and presented 2 weeks ago. Humans are thankfully optimistic, right? The people in this room and those of you online are probably on the extreme end of optimistic, right? So we are going to have to enjoy that and rein it in a little bit. So essentially, some of the associated challenges are that we are generally very success-oriented, and that kind of can cause a problem. And so we have to add more margin and cost than we think typically. And we have to develop, one thing I really think a lot about is smart processes, because it's the smart processes that mitigate for errors made by very smart people. The next one is assumptions are necessary shortcuts. Now, we will never have perfect information about everything. So we have to make assumptions. That's just part of the game. However, assumptions can be wrong, and if you find out too late, you're in trouble. And so before testing your technology early and often, I like to test assumptions early and often, and we do that at every opportunity. And the last one is communication is really the key to everything. I can trace every challenge I've ever had on Sparks to a communication challenge, even technology ones. And so really we work very hard to ask lots of questions and make sure that everyone's voice is heard, and to run effective meetings and reviews, because it's the communication in those forums that really matter. Okay, so my next 3 slides are discussion questions for this week and for the future, because I want to make sure that we are asking the right questions and thinking big as instructed in our emails by Jason. So this one will probably has no cons. The next 2 will have pros and cons that we can then debate. This one is discussion about training. We need to take a more active role in training our mission leaders and our mission team members. We heard about a couple of things. Yesterday, Jeff mentioned the NASA PI Launchpad, which is a great new initiative. It is to help people with ideas try and get through the proposal process, right? And there's also the NASA Astrophysics Mission Design School, and we at Arizona State University have also developed a SciTech Leadership Certificate specifically to teach some really fundamental basic leadership skills that everyone needs for all sorts of aerospace challenges, aerospace projects, but including mission work. And so our first 3 modules that are launching in September is leadership and team building, project management, and finance and contracting. These are things that we all have to learn on the job, but maybe you don't have to learn everything on the job, and you can actually take a course to do it. So that was our goal there. So the question for discussion here is, I want us to think about what leadership, management, and team building skills do we need to develop explicitly, not just hope that people are good leaders or they're a born leader. You know, people can learn these things, and we need to explicitly talk about them and teach them to our future mission leaders. The next one, I've already talked about, this complementary science and pairing small and medium class missions with the Habitable Worlds Observatory. I think there's lots of good science cases there. I understand there's technology risks potentially that people are afraid of combining things together. But at the same time, I also think that these, by offsetting some of the work, right? Habitable Worlds Observatory itself doesn't have to do everything in one observatory, right? You may actually be de-risking things by offsetting some of the effort into another smaller, much cheaper mission. So the question here is, what Habitable Worlds Observatory science would greatly benefit from a companion small set, or 2 or 3, as I said? Okay, think about these. We can talk about it at the end of the session, or at the end of my talk, or just throughout the week. And lastly, this one's not going to be popular. But I think because dedicated small mission funding is hard to make sure that the current program actually supplies the information that we need for Habitable Worlds Observatory, that I wonder if we should really be including plans for dedicated small and medium class missions in the development costs of Habitable Worlds Observatory itself. I know that's not going to be a popular one, but I think it's really important. And just to remind you, these circles are to scale, right? So we have already an idea of what it takes to run 10 to $300 million missions. Now, if you put that next to the $11 billion of a potential Habitable Worlds Observatory, right? It's just a few percent, like literally 5% at most. Okay? So I really think that these small, medium missions have an outsized impact and are actually the investment we need to be making. It's a cheap investment, and thinking small lets us think big. Thank you.
Okay, questions in the room? Julie, did you have a question about that?
I agree.
I told you she was convincing. Do you have any? Oh, Mario back here.
Yeah. Mario Gennaro Space Telescope, Science Institute. So I think you started, I had the question in mind, and you put a slide on the one before you said, the one you said it's unpopular. If you can go back a couple of slides. I'd like for you to give us your perspective on how much this effort of precursor science and technology development need to be completely intertwined. I would think that some precursor science doesn't need technology development and assume the risks of developing new technology in new CubeSats or smallsats. On the other end, some new technology doesn't need to demonstrate any science. No, you want to fly a new device and see that it works in orbit. Is it truly necessary to have these two things go together, or would it be more efficient in some cases to separate? And I'm saying that because in some cases, I would think that the same way CubeSats are modular, they've reduced cost to fly, commercial applications. We could have modular telescopes, some detectors and things like that to do precursor science, and you don't need to develop a completely new small mission all the time to do that. I think we are reinventing the wheel many times with these small missions. Is there a different approach, in your opinion, to doing that?
Yeah, that's a really great point. I agree that they could be decoupled. That's something that people at NASA and program officers have to kind of decide. Should we be decoupling them? How to sell it to a review? It's also a matter of selling things to a review panel. So the question is, how do you choose those reviewers and what kind of instructions do you give them? We typically, as reviewers, get instructions of science comes first, technology second. You could give reviewers other instructions. I don't think it matters. But I think that you said a key word that's very interesting. You said modularity, or you said modular. And that is often talked about as one of the keys to the success of mega projects. If you can find modularity in mega projects, and the fail fast model, you break something quickly, learn from your mistake quickly, and then rebuild it, that's really valuable too. So we can use the small sats in a modular fail fast mode in order to answer that and decouple precursor science and technology development. I mean, I think I'm okay with decoupling it. It's just a matter of whether we have resources to decouple them.
Aki Barbersh, Goddard. Yeah, I want to follow on to that because it's like a notorious problem in this suborbital and small sat stuff is that it's really hard to do tech dev there because it has to do science. You can't win if it's just technology development. So I feel like we don't, and STMD isn't really helping here. So we don't have calls that are just pure tech dev, don't have to do science, and these would be really valuable, and we just don't do it. And I don't know, headquarters, like do something.
We tried it. It was the New Millennium Program.
And what happened? Okay, so Eric Smith said we tried it. It was a New Millennium Program. What happened? Okay, I need to hear more about that story. But
Maybe try it again.
Okay. Why? Okay, and Eric Smith says we tried it. It didn't work. I want to know why. And just give him the microphone.
Iron engine, space pathfinder, so So the New Millennium Program was a program where you proposed technologies and not science objectives. And it ran for a few years, but I was never part of that program, so I don't know the formal reasons why it didn't end up sticking around, but it was not deemed a successful program ultimately. Other people said, and I'm actually of this belief too, if your mission needs technology, that's where you develop it because you have more incentive to make it work than anyone else. Just the general technology philosophy that STMD carries, useful for things like batteries that everyone needs. They've never really given much to science.
But the selection criteria for the small missions are directly opposed to developing any technology.
100% true.
So can we change that at least? I mean, we have our technology risk in our biggest missions, not our smallest missions. That's what needs to get fixed.
Okay, so I appreciate the discussion. Josh has been waiting. Lee has his hand up, and then we do have a speaker here who's willing to answer questions.
Time, it's okay.
I have a question for the speaker. Hi, this is Josh Pepper from NASA headquarters. So you've made a really compelling point for the value of these small missions for HWO. Many, not all, but most of the examples that you cited are missions that will do very specific, very pointed observations of a small set of targets typically. But HWO is going to have a relatively larger number of targets. How essential is it that we think of these small medium missions as capable of observing or probing all of the potential HWO targets as opposed to a few key ones to understand certain kinds of physical processes? Basically, how much should we think about this as a sort of survey of the targets versus answering very specific questions about specific stars and systems?
Well, ultimately, what that would require is understanding what you're trying to learn from Habitable Worlds Observatory, right? So what are you trying to learn, and what is the information that you're missing? And if all 1,000 targets require that information, then we build more small sats or one mid-X or whatever, mid-X level, whatever it is, then we do what we need to do. If one target like the sun turns out to be enough and we just put everything at looking at a sun-like star, which we know our sun is not average, right? Then we just do that. But we need the science community to tell us what is the experiment we're trying to do, what are the input variables that we need, how well do we need to understand them, what is the actual impact, and can we do this in a timely manner? Yeah, so I don't know the answer. It depends. Depends on the science experiment. But I encourage all of us to think about what is the science experiment and what does the experiment need to get an actual answer. That's the problem. Vicki got a question earlier today about doing something that's easy to do but provides less information, right? That we don't necessarily want to be playing in that pond right now. Not today, at least. Right.
Yeah, Lee Feinberg from Goddard. So, two thoughts. One is just a little bit of, maybe there's a lot of people here may not remember this, but early in JWST, we were going to try and do some space demonstrations of technologies. There was this thing called ISIS, was inflatable sun shield. There was a desire at one point to do a test bed that was actually geared towards habitable worlds. I forget the name of it, which was a segmented, isolated test bed that never flew. A lot of these get very expensive and don't fly. So that's the risk. At the same time, I want to support some of your ideas in the sense that, there's different levels of technology. It's true that small sats it's hard for them to have the money to take a low TRL to TRL6. But if there's a TRL6 technology, this is a technology that's kind of been demonstrated on the ground, and it needs to get to TRL9, this might be a perfect opportunity. And a classic case of this are these UV coatings, these lithium fluoride, protected lithium. I mean, it'd be really nice to get space heritage. We're talking about putting these on our next generation observatory that they've never flown in space. And that's something that could do science. So there are probably some really key nuggets. And I'm curious, have you thought about the TRL aspect of this and which TRLs you're gearing towards?
100%. I think the TRL aspect is probably the biggest part of technology demonstration in the small sats. And I do think that we have to strategize. We have to sit down once we have the architecture in place and the plans for Habitable Worlds Observatory is to strategize what are the technological demonstrations we need to make ahead of time and do that well. And this is another reason why I'm advocating to having separate missions devoted to this, because then at least we are guaranteeing the information that we need ahead of launch. Whereas if we go through the normal calls, like the normal APRA Pioneers calls, there's a risk that someone's not going to put in a proposal that NASA needs for Habitable Worlds Observatory. It may put in a proposal that is not very good, so a review panel doesn't want to fund it. It may be on the wrong time scale. Like, I think this came up actually at lunch yesterday. We were talking about the TESS as a precursor, right? So TESS is an excellent precursor for JWST because the time scales all worked out. If JWST launched 10 years ago, TESS wouldn't have been a very great precursor mission for it. And so we need to kind of have a strategy of how to plan in time and in space and in wavelength and in technology importance, the whole thing, which is why I think we need to look at it as a collective.
Okay, I think we better close down this discussion and move on to the next speaker. So any further questions for Evgeny, you can ask them on Slack. And then we're also having a couple of community preparation sessions on Thursday, where I think it would be interesting to continue this thread about small mission precursors for HabWorlds. So the organizers of that, I hope, are listening. I'll follow up with them later. You got your mic on, Christine?
Testing, can you hear me? Excellent.
All right. Well, I don't know about you, but when I think about disks, here at least, I think about Christine Chen. And she was the unanimous choice of the SOC to describe to you everything we know or want to know about the formation and evolution of exoplanetary systems from the point of view of their debris disks. So take it away.
Thanks, Jason, for that really kind introduction. So when Jason gave me directions for this presentation, he said, "Oh, please tell us about all the great science for debris disks, but don't forget to tell us about debris disks as a background source, because when we try and go characterize planets using Habitable Worlds Observatory, the dust is going to be a confounding factor because it's going to create all this noise against which we have to detect planets." And so I have an auxiliary title for my presentation. Oops, too far. How I learned to stop worrying and love debris disks. So I say this affectionately as a debris disk advocate, and I hope to convince you that there's a lot of really great science that can be done by studying these objects. So the image that I have here is a multi-wavelength panel showing observations of Fomalhaut from the short wavelengths on HST on the left-hand side to ALMA at the longer wavelengths. And you can see this was part of an article that appeared in the New York Times about Fomalhaut JWST observations at 25 microns. And I wanted to emphasize sort of the complementarity of HWO with other facilities. And so as I look at this particular panel of observations, I see dust scattering light at the shortest wavelength and thermally emitting at the longest wavelength, with the dust grains out here being the largest ones that stay sort of near where they're born in planetesimal birth rings. And the really fabulous sort of gains that are made by JWST in terms of trying to not only detect the planetesimal belt, but then also to see all of this extended structure from dust, particularly from the asteroid belt, which was not seen at longer wavelengths. This is really a bare photosphere here. And then the dust is actually moving around in here as well. And I'll talk about the dust dynamics a little bit later. Whoops, sorry, I'm having problems. So when I think about exoplanetary systems, this is the picture that I have in my head. And so we've heard a lot about planets, both Jovian planets and then also terrestrial mass planets. But I think of systems that are much more complicated and rich, including planetesimals, planetary embryos, so possible asteroids and comets. In these systems, the young systems, they have very high surface densities, and so they can collide and produce dust, which we detect through remote sensing. So I think there are advantages to studying these particular objects. In particular, there's two I can think of in particular. One is that when we study planets, it's really hard to understand in detail what the composition of the planets is. We learn about their mass and their radii. And we also learn about their atmospheric composition. But one of the things about busting up planetesimals is that you can do remote sensing on the bits and then figure out the chemical composition, and so what the building blocks are actually made out of. The other thing that's nice about the dust is that they serve as test particles, and they gravitationally interact with the planets, and so the planets sculpt through the dust. And so it gives you an opportunity to search for and find things that are lower mass than you would be able to find otherwise. So, for example, detecting and characterizing Plutos is beyond our capability at the current time, but something as small as a Pluto could carve a structure in a dust disk, and you could detect it indirectly that way. So I'm going to try and talk about three things today. One is the connection between planets and debris disks. Second, the composition of planetesimal building blocks. And finally, because Jason asked, how disks impact the detection and characterization of directly imaged planets. Okay, so one of the things I think is really beautiful about debris disk systems is when you look at them at higher and higher angular resolution, you see structure that is indicative of the presence of planets. One of the most famous examples that I'll talk about is Beta Pic, which is shown in these two panels here, E and G. The panel E here shows a scattered light image, and you can see that there's a warp in the inner part of the disk. This is a millimeter image, and you can see it's asymmetric, but there's other structures that people see as well. This is HR 4796. It has a very narrow ring, and it's thought that that ring is sculpted by shepherding planets or lower mass objects. You can also see that some of these systems, they're eccentric. These two are probably eccentric, so that means that the orbits of the planetesimals are actually eccentric and the stars at one focus. And so you need something to force the eccentricity of the planetesimals, and so planets are an obvious candidate. As I've mentioned, for a lot of these structures, astronomers have gone in to try to model the geometry in detail to try to understand what are the range of possibilities for creating them. And so this is a nice paper by Evgeny looking at different ways that you could create the structures that are seen in debris disks. So I think everybody knows the story of Beta Pic, but I'm going to retell it just to be all on the same footing. Beta Pictoris is an archetypal debris disk that was discovered with IRAS in the early 80s. And it was first found to have an infrared excess. And then high resolution scattered light imaging of the disk revealed the warp. This happens to be an HST ACS image of Beta Pic, where the primary disk is seen here, and you can see there's a tilted disk here, the secondary disk, which is about 5 degrees canted compared to the primary disk. And when it was originally found, the location of this secondary disk was used to constrain the possibility of a planet in the system. So it could have been anything from a brown dwarf at 3 AU from the star to something that's several Earth masses that's much further out. And subsequent direct imaging of the system has now revealed the planet that's creating this warp, we think. This is a composite image of VLT data where you can see the disk in scattered light. It's been taken with a coronagraph, and you can see in the interior 2 epochs of the detection of the Beta Pic B planet, one on either side of the star. So we're seeing orbital motion here. So we now know that this is about a 10 Jupiter mass planet orbiting at about 10 AU from the star. So one of the things I wanted to point out is that as we try to study planets that are fairly young, we are inevitably going to encounter systems that are dusty. And just for context, this is a reminder of the timescales on which planets, both Jovian planets and also terrestrial planets, formed in our solar system. So this is a nice figure from a review paper from Halliday and Knupp. You can see the time axis here going from 0 to 8 million years, and you can see the time scale for the formation of Jupiter and Saturn in our solar system. So we know that the core of Jupiter formed by about 1 million years, dividing the leftover planetesimal bits into a non-carbonaceous and carbonaceous-rich 2 separate reservoirs. And this happened probably by 1 million years from the hafnium tungsten dating. And then we know that completion of the Jovian system and Saturn systems occurred from 4 to 6 million years based on aluminum-26 modeling of the moons. And if we look at the formation of Earth, this process was much more extended, taking much more time. So you can see the time axis here going from 0 to 250 million years. So even though the giant planets have formed, it still takes some time for the terrestrial planets to form in relatively within collisions. And so you can see essentially here it takes, you can see the moon forming event at about 100 million years, and the late Veneer here at about 150 or so. And I just wanted to remind you through showing you this beautiful lunar reconnaissance orbiter map that if we look at the surfaces of terrestrial planets, that we see the cratering record, which tells us that collisions occurred at much later times in addition to the ones that formed the Earth. Okay, so returning to Beta Pictoris, one of the things that was unanticipated when it was originally observed was the discovery of CO gas. And the CO gas and gas in debris disks is important because it can tell us about the composition of the planetesimals. So at the top, again, is the HST image, and then you have ALMA millimeter continuum, and then CO observation here as well. And you can see that the millimeter continuum is more compact, and so these are the large grains sticking close to where the planetesimal belt is, and these ones are the ones that are radiatively driven out of the system. The CO is notable for not only being there, but then also being asymmetric. So there's a couple of theories for why there is CO, or why there is this particular geometry in the system. One is that the system has experienced a giant collision among volatile bodies, which has released the CO gas. Another is that there are planetesimals that are trapped into a mean motion resonance of an undetected planet, and the mutual collisions within the mean motion resonance create the gas that's seen. Since that time, there's been about 24 objects that have been discovered to have CO gas. This paper by Quinton Krall was written several years ago when about 12 targets had been detected. And so our understanding now is that the CO is collisionally generated from probably volatile rich planetesimals. And you can tell this from looking at a population analysis of these targets. And so on the y-axis here, we have stellar luminosity. On the x-axis, we have distance from the central star. So at the top, you have stars that are massive, that have much more UV radiation compared to the ones at the bottom. And so the UV is particularly good at photodissociating CO. And so basically, this green area tells you where the photodissociation lifetime for the gas is less than 10 years. And so it would be expected to be destroyed rapidly. On the left-hand side, this part shows you the temperature, the black body temperature for the parent bodies. And so in this particular region, if you're too close to the star, the parent bodies, the planetesimals, would have temperatures over 140 K, so they're likely not to be able to hold on to the volatiles. And so they noted essentially this is the phase space in which you're allowed to have CO-rich debris disks. But the gas has been detected not only in CO, but in atoms as well. This happens to be data showing the sodium D1 and D2 lines. And in this particular experiment, the slit is aligned with the disk, and then the velocity is dispersed in the x direction. And on the model, you see on the left, you see a model for the Keplerian rotation of a disk. And you see that essentially what you're seeing here is Keplerian rotation of the sodium D1 and D2 through the resonantly scattered sodium. And actually, there have been a number of atoms that have been studied this way. This is for beta pic. So what can you do in the ultraviolet? So the ultraviolet is a wonderful wavelength to work at because it provides a lot of complementarity in terms of richness for atomic lines. And so the figure on top, this is a STIS spectrum for a young star called Eta Tel, published by Alison Youngblood. And the thing that's notable here, if you look at the top, is all of the atomic lines that you have access to. And you notice that for each one that's marked out, there's an absorption feature. And so what you're seeing here is absorption from circumstellar gas along the line of sight. So in this particular system, what's thought to be happening is that there's a star, there's an edge on disk, and so essentially you're seeing absorption from the gas along the line of sight. And so the carbon and oxygen in particular can be characterized at UV wavelengths. And carbon and oxygen are, extremely interesting elements because they tell us about the chemistry of the planets. So, for example, in our solar system, we live in an oxygen-rich system, but there are many different possibilities that could exist. One of the reasons why we think that that's true is because of the formation of Jupiter and that it blocked the accretion of volatile things during the later evolution of our solar system. And so what Alison's done here, this is a really lovely plot showing the abundance relative to iron as a function of element. And so you can see the new paper here shows observations of Eta Tel in blue for carbon, nitrogen, oxygen, magnesium, aluminum, and so forth. And she's also compared it here to the sun, and then beta Pic, which is the other system for which these measurements have been well made. And then on the right-hand side, this is the C/O ratio for these particular systems as inferred from the circumstellar gas. So the C/O ratio, increasingly has been a really interesting metric that people have used to try to understand where planets form. So one of the thrusts of Jwst research, for example, is measuring the C/O ratio in planetary atmospheres to try to understand if we can make a connection to disks and snow lines to understand where those planets formed. One of the drawbacks to looking at planets is that when we do spectroscopy, we're looking at the upper layers of the atmosphere. And, for example, Jupiter and Saturn, they're not really well mixed in the atmospheres until you reach 20 or 30 bars. But in looking at busted up planetesimals, it'll give you a good sense of what the bulk composition is, and then constrain where the things form. And the other thing I wanted to point out briefly was that in addition to seeing these stable components, you can see time variable absorption toward these debris disks as well. And so this is a snippet of a sodium-1 spectra for beta Pic taken over multiple epochs. And here you can see the stellar absorption feature, and then these narrow features here are circumstellar gas absorption. And this is the stable gas that we saw in Keplerian rotation, and these are time variable events that correspond to exocomets. Really excitingly, there has been monitoring of beta Pic using TESS photometrically. And in the TESS light curve, there's this really interesting structure that's been picked out, and it's understood to be a comet falling into beta Pic with a coma and a tail structure. So, I think the potential for learning about infalling comets is really exciting. So I'm going to pivot to the last part, which is what Jason asked me to talk about, which is how dust impacts the detection and characterization of planets. So one thing that I tried to say was that young stars are dusty, and so if you want to study young planets, you might have to deal with some of this dust. And so this plot is sort of a summary showing the 24 micron axis as a function of age, and each one of these dots represents a planetary system or a star. And so in general, the expectation is that the upper envelope of these infrared excesses goes as 1/T, because 1/time, because you exhaust the planetesimal belt, the reservoir, over time. But there are some systems that appear really, really dusty. And Kate Sue has been monitoring these with, she was using Spitzer IRAC and SOFIA as well, and she noticed that they were very variable, which suggested that they were actively undergoing collisions. So you could monitor the activity and see the collisions happening in real time. So one of the things that I wanted to reiterate was that the dust in these systems is transported. It doesn't necessarily stay where it is created. And I talked a little bit already about radiation pressure, how the little dust grains can act as sails because, radiation from the star impinges on them and blows them out of the system. But another possibility is Poynting-Robertson drag. This is a relativistic effect in which an orbiting dust particle feels a headwind of photons from the star, and so it loses angular momentum and it spirals into the central star. And so, these debris disk environments are expected to be busy with like particles moving in different places. I gave you an example of beta Pic where you could see how the dust grains moved around, and I just wanted to point it out again for the Fomalhaut image. So here is the ALMA image shown in red, depicting where the large grains are, and then the blue is the HST scattered light image, and you can see that the small grains are indeed exterior to the large grains, indicating that they're being driven out of the system by radiation pressure. And then the really beautiful thing about HST is its wonderful sensitivity, which allows it to see not only the planetesimal belt ring, but then also the dust interior and exterior. It's just much more sensitive. Okay, so what does this mean for trying to detect planets in disks? There's a GTO program here at Space Telescope to study Beta Pictoris using Jwst, as many modes as we can get our hands on. This is work that is led by Jens Kammerer, who's here in the audience if you'd like to ask him any questions about this. But this is, I think, a positive demonstration of recovery of a planet in the face of dust. You can see here, this particular source was observed with 6 different filters with a NIRCam coronagraph. So you can see the central star is occulted here. And then you can see these very nice high signal noise detections of the B component. And Jens has done this very nice modeling of not only his new photometric points, but then also data in the literature, both spectra and photometry. And it looks like the coronography, the observations are consistent with a bare atmosphere. So I'm a Mary GTO, and I spent my time on, one of the things I spent my time on was Mary MRS observations of Beta Pic. And so I'm particularly excited about the MRS because it's an IFU, and so it gives you a spectrum at each point in the field. And so this particular work is led by Caden Worthen, who's a JHU graduate student, and he's in the audience here if you have any questions about this. But on the top left, what you see here, this is a PSF subtracted cube. So this is reference PSF subtraction, and so you can see the light from the central star is suppressed. And this is an amazing achievement in the sense that this instrument was not designed to do this. And so at half an arc second, you can see clearly the detection of Beta Pic B. Caden has extracted this very nice spectrum for the companion. And so that's what's shown here with the black error bars. And then here's an L-band photometric point from VLT with a notional atmospheric model overlaid. So this is super cool because it's the first detection of water in the atmosphere of Beta Pic B. Caden has been looking at this data in more than one way. So this shows you the reference PSF subtraction, the classical PSF subtraction, but he's also been applying SDI techniques too, so cross-correlation with atmospheric templates, both, for like a 1700K companion, which is, this is understood to be, and also looking at cross-correlation with particular molecules. And so in that way, he's also been able to detect water through the cross-correlation at the full resolution of the cube, compared to in here with the reference PSF subtraction, this data is binned to make it easier to extract the planet. Okay, and so I think, unfortunately, probably what Jason really wanted me to talk about was this. There is an ExoPag SAG group, which is really exploring this area, and they're taking a multifaceted, very systematic approach to understanding dust in different environments, and for example, like debris disks, and how that impacts planet detection and characterization. So the leads for this are John Devis, Yasuhiro Hasegawa, and Issa Rebolito. John has a poster at this conference. I encourage you to speak to John. And you can see that they have this, again, very systematic, very thoughtful approach to this problem, looking at everything from observations. These are the titles of the research areas and then the leads. So everything from observations, photometric of infrared excess to like interferometric observations to try to understand the hot zodiac content, to looking at the dynamics of dust grains and what the expectations should be based on the data that we already have, to understanding things like, post-processing, some of the things that I've shown you. And I wanted to highlight that they're organizing a workshop here in Baltimore in September, the impact of exozodiacal dust on exoplanet direct imaging surveys. This QR code will take you to the ExoPag-SAG 23 webpage, and it has a link to the workshop if you're interested in attending. And again, I encourage you to talk to this group. So this is my summary. Thank you.
Remember where I left the microphone.
There's one right there.
Oh, there's one. Thank you, of course, Christine. Well, Aki really got on the ball there, so I hope she agrees with you.
Okay. Of course I do. Aki Berberish Goddard. Thank you, Christine. That beta pic B stuff is so sweet.
Yeah.
What do you mean by bare atmosphere, though? What does it mean?
I meant that I meant that, so here and here, right? So Jens is here, so he could talk to his model, of course, and so is Caden as well. So I don't know, maybe.
Can we have Jens say a few words?
Yeah. Let's have Jens say a few words.
Well, so I guess what was meant is that we just fit an atmospheric model, and we can successfully remove the component of the disk, basically. Because in those images, for the first time, we can see both the planet and the disk in the same dynamic range, basically. But it's possible to kind of remove the impact from the disk and get photometry that's consistent with just the model of the planet itself.
Okay, great. Thank you. That makes sense now.
Any questions in the room here? Alex, anything online? Okay, anybody else in the room? Vanessa. I'm not brave enough to throw it.
I'm not coordinated enough to catch it. So thanks for a really nice talk. I was wondering if you could comment in terms of the design of a HWO chronograph. How important do you think polarimetric capabilities are going to be, and what precision would be interesting to you?
Yeah, so polarimetry is near and dear to my heart because there are constraints that you can get from polarimetry that you can't get from any other way. And, I think it was a little bit unfortunate that, Jwst isn't designed with some polarimetric capability. But essentially, when we're studying, for example, dust grains, there are certain degeneracies. So we try to approach it from a multi-pronged sort of technique where, like, for example, scattered light will give you a set of constraints, like thermal imaging gives you another set of constraints. And it's a really complicated field, and so having the polarimetry is actually very helpful for distance, because we have all of these things, particle size, particle shape, porosity, composition, and it's a really nice handle that's complementary to the others for disentangling those things.
Yeah, so this is lovely. This is Chaz Speichman, JPL Caltech. This is a lovely test bed to be able to say, okay, I've now detected beta pic B. How far down could I go in planet brightness and still pick out B in the presence of the dust? I mean, when does the dust become the limiting factor?
Yeah, so we haven't done that yet. And part of it is, we're scrambling like mad to get this published. But I think you raise a really good point. which is something that, should be included in analysis and would be helpful for pointing toward the future. The other thing that I wanted to point out, though, which I said, but I wanted to highlight, was that I think originally, maybe when 15 years ago, when we were thinking about studying planets in, using chronographs, in the presence of dust, I think we thought about it a lot photometrically. And so in that case, you really have the dust in your aperture, right? And it creates this noise source. But, it's been really inspiring over the years to see people apply different high contrast techniques, especially when you have high spectral resolution data, right? And when you have high spectral resolution data, that gives you the opportunity to look at lines in the atmospheres of planets and to do cross correlation to pick out different molecules, whether it's water or CO. And so I think in that particular case, the dust becomes much less of a problem because it's really a continuum source. Whereas the molecules are lines and you pick them out through cross correlation. And so I just wanted to, make sure that that point was heard and understood, because I feel like sometimes we're still stuck in 15 years ago.
Pen Chen from the Exoplanet Exploration Program Office. Thanks for a beautiful talk. So what are the timescales of variability in exozodi brightness? I'm asking in the context of think about how our ability in chronograph images to subtract that out, and also it plays into observing scenarios.
Sure. So for the most active systems, the ones that Kate has been studying, she's been monitoring them with several epochs in a year. And so, for some of these examples, you can see the collision occur, and then you can watch the time scale of the decay of the excess emission. And what's been really striking about it is that how fast the decay is, essentially. So, from theoretical modeling, I think most of the expectation had been it would take hundreds of years to go away. But what she's actually finding is that for some of these systems, it's actually gone, it's returned kind of close to a baseline in a couple of years. So it can actually be fairly fast.
Take back what I said. We're going to have one last question from online.
Yes, it's more to Jens even, from Carl Stubblefield. Does Jens have limits on the circumplanetary disk around beta big B?
It's a yes or no question. Yes.
Circumplanetary disk.
No, the answer is no. He does not have limits. So sorry about that, Carl. All right. Thank you, Christine. Again, let's thank her.
We will be back at 11 for coffee.
Or after coffee.